So our next speaker is George Whitlinger, correct? And he will be talking about HDF use in long-term energy monitoring systems at the U.S. Energy Information Administration. Well, thank you. We'll just give 5 minutes.
Thank you. Good morning, everyone. My name is Josh Whitlinger. I work for the U.S. Energy Information Administration as a mathematical statistician. I've been there for about 2 years. I work for the Office of Integrated and International Energy Analysis. And today we're going to talk about the use of the HDF5 here at EIA. So first of all, while I try to get my screen on this, I want to show up. There we are. We'll go over a little bit of an overview of the EIA products that the Energy Information Administration puts out. We'll talk about the current use of HDF5 here at EIA. So the current work going on to put that into our national energy modeling system and future work and open questions that we have currently. So first of all, what is the U.S. Energy Information Administration? Well, U.S. Energy Information Administration is a statistical and analytical agency within the U.S. Department of Energy. The EIA is the premier energy source of energy information, and by law, our data, analyses, and forecasts are independent of approval by any other office or employee of the U.S. government. So what are some of the products that we put out here at EIA? Well, the short-term energy outlook, which is a monthly forecast of U.S. and global supply, consumption, trade, stocks, prices, and energy-related carbon dioxide emissions, with a horizon from about 12 to 24 months. A lot of people look at that for exactly what's going on in short-term outlooks. You'll see that very often. The product I work on mostly is the annual energy outlook, also called the AEO. The AEO is a product that provides U.S. energy supply, consumption, and trade for over a 30-year period. This is produced using the National Energy Modeling System, which is what we'll talk about at the last part of this presentation. The International Energy Outlook, the IEO, is our global version of the AEO. So it projects the global energy supply, consumption, and trade over a 30-year period. That's produced via our World Energy Projection System. And then a few other products that we put out are the This Week in Petroleum and this Natural Gas Weekly Update. Those summarize things that are going on currently with weekly developments in those respective markets. Today in Energy summarizes our various topical energy trends that's published on our EIA homepage. And then, of course, as part of the U.S. government, we also do some reports for Congress and key stakeholders when they have questions coming up about different policies that are coming out and policy questions that they may have. So let's talk about the two large modeling systems that we mostly deal with, the AEO and IEO. You'll notice they have modular structures. So the National Energy Modeling System is an energy economy modeling system of U.S. energy markets for the period extending through 2050. This model projects the production, imports, exports, conversion, consumption, and prices of energy, subject to a number of assumptions that we do. The assumptions encompass different macroeconomic and financial factors, world energy markets, resource availability, and cost, behavioral and technology choice criteria, technology characteristics, and demographics. In other words, a lot of various assumptions. NEMS produces a general equilibrium solution for energy supply and demand in the U.S. energy markets on an annual basis. So our Office of Energy Analysis develops and maintains the National Energy Modeling System, and analysts perform policy analyses requested by decision makers in the White House, U.S. Congress, offices within the U.S. Department of Energy, including program offices and other government agencies. The real interesting thing for you all to remember while we go through all this is NEMS was first introduced in 1994. So this is a very legacy system that we're dealing with. The World Energy Projection System, on the other hand, generates projections of energy consumption, prices, production of the IEO, or our International Energy Outlook. WEPS is also a modular system and is made up of a number of separate energy modules joined through a common database, which enables them to communicate and work together. We develop each of these modules independently and incorporate them with well-defined guidelines and protocols for system communication and interactivity. So just a real quick, you can see on the NEM side, we have our supply modules that run first, our conversion modules that then actually convert from supply to demand, and then our demand modules through transportation, industrial, commercial, and residential. And this all actually works to build our national energy modeling system that runs modularly. Similarly, on the WEPS hand side, you can see that we do a supply, conversion, and then demand. And this actually runs through all sort of modularly as well. So both models are modular, composed of heterogeneous modules representing different aspects of the energy system. They're partial equilibrium models with macroeconomic feedback provided by a third-party macroeconomic module. Solutions are accomplished by running each model iteratively until incremental changes fall below a set threshold that we have. Each module can have its own internal structure. And within both models are modules of which are constrained as LP optimization modules, logic models, and simulation modules. Perfect foresight is generally used. And although some of these may use myopic foresight, and most modules impose a hurdle rate of investments that reduce the impact of far future on capacity planning decisions. So NEMS is a very detailed representation of the substructures of the US energy system, but it has limited interaction and limited representation of trade with the rest of the world. WEPS represents the world as 16 regions with trade between them, but no region is modeled in great detail. So remember the big thing of this is these modules do not talk to one another. Each component is standalone, meaning that you can pull it out, run it on a standalone, and all the communication works through a centralized data file that we call at EIA the restart file. And the choice of that format for the restart file really matters, as you can imagine. We'll go into more detail about how this runs differently in NEMS, as NEMS has a lot more I/O operations compared to WEPS. So let's first look at the WEPS modeling system. If it will let me hit the slide, there we go. So overall, WEPS uses an iterative solution technique that works towards converging consumption and price in an equilibrium solution. Each module is run independently, but reads and writes to a common database to communicate with other modules. The common database provides seed values for macroeconomic quantities, energy prices, and energy consumption. The system runs each module in turn before running its convergence module, which determines if the system has converged or if it needs to be run again through another sequence. On the screen right now is actually a diagram of how WEPS runs. So here you see we have a preprocessor that reads in data that you may need to pre-process before coming in, usually raw data from some of the sources that EIA uses. Then we go into our global activity market, which is just some global markets that we put together. Then we go through our demand modules of demand for residential, commercial, industrial, and transportation. Remember that all of these are run individually of one another. So what that means is inside of WEPS, you actually run this module. So global activity, for example, from 1990 to 2050. All of that is run, and then it hands off that data to the next module that it will call. In this case, it would be residential. So on and so forth. Each module is only called one time for one I/O operation inside of the HDF that we use for our restart file. So a lot of these are very interesting to talk about. I'm not going to go in depth onto many of these modules as they're not the real main reason that I'm here. But just know that, as we run through these, every time we have one call to the HDF, we read in, and we do all of this via Python and Pandas. So we do many of these calculations in Python and Pandas, and we use the HDF store object to read and write to our HDF. This reduces many of the I/O operations. WEPS takes approximately an hour to run through the full cycle, and a small fraction of that is actually our I/O operation. So WEPS has actually used HDF for about 7 or 8 years now. And it's a simpler system, WEPS, as you can imagine. Each module reads in that shared data from the HDF, processes the information, and then writes the shared information back to the HDF5. Each WEPS model really only writes out dozens to hundreds of data frames to this HDF, but it only has to do it once. So we open it in Pandas, we loop over the writes, and it's fast. But since IO operations are not such a big deal inside of WEPS, we don't really have that many of them, so it's not that big of a deal. So we use many of the utilities which generate an unformatted binary file to interact with one Fortran program. And that's kind of an important factor here because you're going to see shortly why NEMS has a problem. So obviously, WEPS we're very happy with. We love using this HDF, works great, hierarchical data format, great to look at all these values in. And they're not having many detailed variables that are very much dimensionality. We're only dealing with about 3-dimensional variables in those cases. So we wanted to integrate all of this into our domestic modeling within NEMS. So just remember, WEPS hits that restart file one time. NEMS is built quite differently. For any of you who programmed in the 90s, you couldn't really do all those types of things. So what we had to end up doing was talking about a little bit of the challenges that NEMS does. NEMS does not run all modules individually. What NEMS does is it runs all years individually, but all modules in that year. So to reiterate what that means, think of it this way. It's 2022, first time we're maybe putting in some new data. So our macro activity module runs, and that might run in 10 seconds. Well, after that 10 seconds is up, it calls the next module and the next module. So all of our supply modules might take 10, 20 seconds to run, which for a year might not be that bad for 2 to 3 minutes for all these years, but you're calling 12 modules. This is all based in Fortran as well. So imagine now we're not dealing with Python. We're not dealing with a lot of the wonderful tools that we have built inside of Python. We're dealing with Fortran and Fortran 77 code that some very nice person wrote up and then didn't document. We've all been there. So NEMS presents a lot of these challenges that are encountered beyond WEPS. So it's built around an in-memory Fortran architecture, as the spine of this is in Fortran. So as you imagine, that makes debugging very difficult, particularly because NEMS is actually written in multiple languages. It's written in Fortran, Python, GAMS, AIMS, and a few others. Further, we iterate rapidly between data-intensive modules and must complete all I/O and calculations in that span for 1 year, and then repeat this for every subsequent year. So to meet those speed goals, NEMS currently is actually written in a format that writes out to an unstructured data file. So what does that mean? Well, we write out a binary data file that has no metadata whatsoever, but there are some files that tell you where things are. If you want to know what the gasoline was for 2002, well, that's character 200, 212 in this unformatted binary restart file. Yeah, it's really great to read in your free time, by the way, if you're just trying to read through numbers. So we worked on a modular modernization effort. So AEO 2023, you can see we have a restart file. We have a program called Filer, which is a Fortran program that understands where all these things are in a binary restart file. And then it can write out to other formats. Using NumPy's F to Pi code, we actually investigated a way to leverage Python and now can actually go from an unformatted binary restart file to an HDF. So that's great, really cool. Honestly, really exciting. So we're trying to move into actually integrating this HDF into the AEO. But we have some problems with that. We're working with 3,728 variables that are all dimensioned kind of insanely. There are 3-dimensional, 4-dimensional, 5-dimensional matrices that you're putting in there. So to give you an example of what that looks like, let's use one variable. In EMM, which is one of the modules we use, there's a 5-dimensional variable that is 3 regions by 12 fuels by 61 years by 4 types by 2 methods. So writing this out into an HDF takes about 20 seconds each time. When we write this out in an unbinary formatted file, taking all 3,728 variables, we write out in 1.5 seconds. So obviously you see we've hit some kind of wall here and we can't figure out why. So part of the problem is, obviously, we're crushing these all down because we have to write back and forth from an unformatted binary file to this file. And part of the problem is we have to smash these down into small tables to be able to write back and forth. So we're writing 2,196 4x2 data frames with all these different labels inside. So with that, I came here today to learn some about how to use an HDF more. Obviously, we're still learning this as we're new here. And we're trying not to edit the current IO structure of NEMS because that would be a major overhaul that we haven't gotten to yet and quite honestly haven't had the time to even investigate yet. So without editing, running every year, but module by module by module by module, are there methods we can use to minimize our IO costs while still benefiting from structured formatting in the HDF? Can we structure the data frames differently into this HDF? Are there a better way to do table structures with indices that we're trying to put these in? Is there a time to minimize processing time, writing back and forth from all these Fortran programs into the HDF? And we're trying to explore how maybe changing the spine to a Python program will actually impact these decisions as well. So I look forward to learning more while I'm here with everyone, and thank you very much.
Thank you, George. I'm English here.
So in an unbinary format, it's 90 megabytes. When we put it out to the HDF, it's 1 gigabyte. And that's mostly because of how we're structuring all of these 5-dimensional variables to write out in a hierarchical format. Yes.
I talked to you from your slides that things like pandas, data frames, and Python. Do you have any idea how thick the layer is between your data and the actual HDF5 file in terms of assumptions it's making or the way that it's using the underlying pieces? Do you understand my, in other words, if I were solving the problem you were solving and I was using the HDF5 library API, there's a pandas wouldn't be there, there's a whole bunch of stuff that would not be that way. Do you have a sense of whether or not to move that stuff out of the way, maybe be able to see better results?
We have not investigated that yet, and that's a very great question, something I need to take back actually. Mostly because, as anyone who's ever worked for the federal government knows, making any decision large like that is slow and has to take a lot of precaution inside of this, especially when you're putting out an annual product that needs to be secure and everything. I'm gonna actually investigate that. I'm gonna have to write down that one so we can actually look into it more.
So it is non-trivial to achieve for all cases really good performance just coding the HDF5 API because it's quite a verbose API. But the investment's worth it when you're dealing with issues like this.
Yeah, thank you. Okay, thank you, everyone.
Thank you. Thank you.